Hello, and thank you for joining us. Today's webinar is Analysis of Bottled Water by Teledyne Tekmar Fusion, presented by Tyler Trent, TOC Product Line Manager for Teledyne Tekmar. We will be taking questions, so please feel free to submit your questions throughout the presentation, and we will address them at the end. This webinar is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Tyler Trent.
Thank you for that. Good morning, good afternoon, and good evening, depending on where you are. My name is Tyler Trent. I am the Product Marketing Manager here for Teledyne Tekmar, responsible for the TOC product line. Today's webinar, we're going to address the analysis of bottled water by the Teledyne Tekmar's Fusion TOC Analyzer. So a little bit of housekeeping today. We're going to go through some agenda items. We're going to be talking about the importance of TOC and why do we need it. A little bit about the Fusion TOC Analyzer from Teledyne Tekmar. The study that we did on bottled water, where we looked at 5 mass-produced bottled waters from the local grocery store, and the results that were obtained from this study. So first topic, TOC importance to drinking water. So why is this important? Well, TOC is kind of classified as different types of organic matter or inorganic matter that could be into our water. So when we start looking at that, why do we need to test our water? Well, we need to benchmark our water. So when the water comes into our facility, a lot of times we would like to start collecting TOC information on it, because that shows us if the TOC content is high, that means there could be high forms of biologicals or other materials that have carbon associated with them inside that water. So we would like to start with a benchmark of our water. And after the water gets treated as it goes through the plant and different things occur, different treatment processes occur, we like to test the TOC water throughout this process. If the TOC is high, it could form trihalomethanes, and it would need to be filtered more. So that's kind of done by a couple of different techniques, by TOC and also volatile organic carbons, which is Persian trap. So the water is getting tested in 2 different ways. And one reason, if there are high carbon concentrations and it could interact with some of this cleaning material, it could form the THMs, and they could be also known as carcinogenic. So we want to make sure we have very low levels of carbon and other chemicals in our water. So we continuously monitor this throughout the filtration process. If we see certain levels are too high, we're going to have to go back and remediate more. After the disinfectant process, we want to measure the effectiveness of our purification process as a sign of water cleanliness. Typically, when we look at tap water, depending on your location, it could be less than 1 ppm, but it could range anywhere between 1 to 3 ppm of carbon. So putting this presentation together, we here in Mason, Ohio, which is just a suburb of Cincinnati, gathered a report. This report is from the Cincinnati Water Works, and it's been around since 2018. This is just a random report we provided from us off the internet. When we look at here where we live, our THMs are a certain level. We have a unit measurement of 56.5. It's a byproduct of the drinking water chlorination. So when we start looking at different things like that, well, what could that do, or how could carbon have an impact on there? So when they went and measured the TOC content in the water, please note a lot of the cities will publish these reports and give them out as asked. We can see that we have certain types of highest compliance levels detected of 2.07. So it's it's very low, and it's very right where we need to be. So naturally, it's present in the environment. So we are completely okay. Our water coming into the process facility, coming out of the process facility is safe for drinking water for consumption. So why do we want to do TOC? There's other techniques out there, but TOC is a catch-all. What do I mean by catch-all? And I'll explain a little bit here. But when we start looking at different techniques such as HPLC, NIR, or GC, those could be highly expensive, highly technical, long method development process, or they could be very selective. In some cases, we want to be a catch-all. We don't want to be as selective. We want to convert all carbon over for measurement. So that's kind of where TOC comes into play at. It's inexpensive, easy to use. It comes with preset methods, so very little method development is needed, and it's a catch-all. So what do I mean by catch-all? Well, TOC is a great catch-all because it captures all carbon. Cleaning reagents, bacteria, solvents, pollutants, fertilizers, residuals from pharmaceuticals, pesticides, organic matter, and more. It'll take that carbon in that sample as we send it through certain oxidation processes, converts it over to CO2 for measurement, and we get a one lump sum value instead of having specific and unknowns that we have to go and trace down through analytical methods, analytical standards. TOC provides a great catch-all, one interpretation for what the water is like. So as we talk a little bit about this system, or a little bit about this process, we ran it here on the Fusion. So the Fusion is actually used for drinking water purposes. So it comes with certain methodologies, and then we have certain methodologies that we come compliant to or standardized to, such as EPA methods, standard methods, ASTM methods. And this system is kind of used for certain types of applications: drinking water, purified water, and other different types of clean water. Also pharmaceutical water if needed. So this system, since it's a UV persulfate, it looks at cleaner water. So if you have a sample that might be particulated or heavily particulated, this will not be the right choice of technique. That would be more of a wastewater type of application, and you're going to be looking at a combustion system for that. So a little bit about the system. You know, it has a 75 position carousel that contains the 40 ml Vela vials. These Vela vials are very standard across the whole environmental industry, drinking water industry, as they're used for many other techniques. This system does allow you to run stock standards and check standards from one single location via automatic dilution and automatic calibrations. So that's one great thing about this system. It has a different versatility and flexibility built in. Also, you know, we like to show the system itself because sometimes chemists or lab techs would like to look at the system from far away and say, is my system running? How is it doing? What step is it on? What mode is it in? So that's why we have all the glassware on the very front of this unit. So you can see exactly everything that's happening within the system. You can see that your system is sparging your IC out. You can see that your UV light is interacting with your sample to cause the chemical oxidation. You can notice that your copper tin scrubber is doing its job by removing certain corrosives out of the mixture, your halogenated compounds, and trapping them on the copper tin, scrubbing that material. So it's all there for you. It's right there in front of the system. Also, you know, we have different types of things, different types of features into the system: auto leak checking, accurate flow rates, and optimizing sparge flows for methodologies and things like that. So if you're interested in that material or that type of talk, you know, be happy to reach out to us, and we'll be able to address those questions you might have on that topic. For some laboratories, it may not matter, but some laboratories it does. So when we start looking at the software, it does have different types of features. 21 CFR if your laboratory requires signatures, electronic signatures, and things like that. Benchmarking, auto calibration, auto blinking, and different things like that are added into the software. So it adds a little bit of smart automation and also compliance control for what your laboratory may or may not need. So you might ask, why UV persulfate for drinking water? Well, there's a couple of reasons why. When we look at drinking water, it's typically in the low ppm to ppb ranges. But then when we look at wastewater, we're looking at several hundred ppm. So how do we make sure we pick our specific system for what we're doing? Well, for drinking water, we can look at there is the UV persulfate, and then we also have membrane conductivity that will basically match the same ranges. But with the UV persulfate, you have a little bit higher range due to the type of detector. Well, certain types of systems or certain types of analysis techniques have different types of interferences, but we have certain types of scrubbers built in that allows us to prevent interferences within our system. And then when we start looking at comparison of estimated background, well, when we run a combustion sample or a combustion TOC, you're seeing anywhere between 100 ppb, 200 ppb of background contribution from the catalyst alone. Well, if you're going to do drinking water, you're trying to get the utmost sensitivity and measure down to the lowest ppb level that you can, you want to make sure you choose the right technique there, and combustion may not be the right one. So that leaves us with UV persulfate. UV persulfate has very little estimated background carbon. So it's a cleaner background compared to what a combustion system might be. So when we look at different types of detectors, we have membrane conductivity versus halogens, or sorry, NDIRs. And when we start looking at halogen interferences, obviously THMs contain halogens. And we want to make sure we're measuring certain things so we have clean working water. So what we see here is some of these halogen interferences could have an impact on certain types of techniques out there. So you want to make sure you're choosing the right technique for your right analysis at the time. And for this analysis, it proves to be that a UV persulfate with a NDIR is the better choice because it doesn't have as much interferences compared to some other type of detectors out on the market. So that's why we come back to this slide, and we're going to say, let's choose the UV persulfate for this analysis. So what we did here was we're going to look at a study on bottled water. Everybody drinks bottled water. If you're on the go, if you're traveling, you're in the airport, a lot of people have bottled water in their homes. So what are we testing, or what do we look for in this? So we actually went out and grabbed 5 popular bottles of water. They were analyzed from our local market here in Mason. We wanted to see what type of TOC content was in those samples. As you know, as I said, tap water is anywhere between 1 to 3 ppm, depending on locations. It could be lower, but that's the average that we see. So what we wanted to do first is we kind of wanted to make sure we're starting off with the correct method. So how do we ensure we're starting off with the correct method? Well, the Fusion actually comes preloaded with methods that you can choose. It comes loaded with a TOC drinking water method, a TC drinking water method, a TC minus IC drinking water method. It comes with pharmaceuticals, wastewater, different things like that. So what we did is we opened up the software, we went through and kind of chose our method. Well, we know that drinking water should be in the range of 1 to 2, maybe 1 to 3 ppm of carbon. So that's what we did here, is we looked at our range, optimum range, and kind of set a method based upon what we wanted to accomplish with this system. And that range means we can easily hit analysis from ppb levels up to maybe 10 ppm. And as we go through the method here, and we can change our sample volume, that will dictate and change our optimal range. So more sample volume is going to lower our range, but it's going to increase our sensitivity. We're going to get better sensitivity at the low end because we have more sample to send through the system. But if you have other types of samples, you can also do different types of dilutions and change all the needed acid persulfate volumes that you want to dial your system in. We give you those flexibilities within the method development. So as I said before, we end up going from a 6 mil method to a 9 mil method. Then we also reduced the amount of acid and reagent we're adding to help eliminate some of the background contribution or the background blanks from the system itself or the reagents themselves. And then if you notice up here, as you make changes, the optimum range will actually change for you. So as you make modifications to the method, it will tell you what your optimal range is. So you know exactly, you're pinpointing what range you want to hit. So we started off, basic standard preparization, 1,000 ppm stock standard. From there, we made a 2 ppm calibration standard, and then we put it into the system. The system basically did the calibration for us via auto dilution, and then it also will run our check standards for us. So as we go through and look at this study, we'll utilize a lot of the features of the system itself. The stock standards, you can also purchase the potassium, the KHP, the potassium hydrogen phthalate, from most chemical vendors out there. So it's a pretty off-the-shelf chemical, so it's nothing special that you may or may not need. So for this, here are the 5 samples that we analyzed: brand 1, brand 2, brand 3, brand 4, and brand 5. Obviously, we can't put what brands we're analyzing. It's kind of a market basket survey here. So brand 1 is spring water, but it was filtered by a 2-stage microfiltration process with UV light. Brand 2, spring water, and it was vapor distilled. Brand 3 is also spring water, but it came from a natural aquifer. Brand 4, artesian well water, underground aquifer. And then we had municipal water, and that's done by reverse osmosis. So let's see what we needed to do here for sample prep. So what we wanted to do here is we wanted to, open the bottle of water first, and we wanted to fill the 40 ml Villa vial. For this step, we actually chose low-level TOC vials. So these TOC vials are certified to less than 10 ppb of carbon. We made sure we inverted 3 times to ensure that we're getting a good homogeneous mixture of the water coming out. Obviously, it's bottled water. Then we stored the water in the refrigerator, and then we got rid of it after 24 hours of sampling. Some laboratories like to preserve their samples with 1% phosphoric acid to extend sample lives. If you do this, if your laboratory does do this, what we would recommend is reducing the amount of acid in the method parameters, because you already are acidified your sample less than 7 for stabilization over time. But to remove inorganic carbon within the TOC process, you add acid to bring it down to a pH level of 2 to sparge off that IC. So if you do have a preserved sample, we recommend you reducing the amount of acid added within your system just to help with the sample a little bit better. So testing criteria that we used against this, all standards that we looked at were less than 5%, and the samples had precisions of less than 7%. Obviously, with clean drinking water, bottled water, you have some variation from sample to sample, but 7% is a fair value, and that's what we've seen across other laboratories across the nation. Then when we looked at check standards, we want to make sure our accuracy is good. along with our precision. So our accuracy for our check standards is within 10% of our tested value, and the calibration curve needs to be 3 nines or better. So let's talk about the results now. Where do we go to? How did we get from system setup to sample prep? Now what do our results tell us? And now what are we getting from these results? So here's a part of the calibration results. Everything was ran from a 2 ppm stock standard using auto dilution features on the system, which you can see the dilution scheme that it ran. It went from a straight sample 1:1 all the way down to a 1:75. You see the precision percent RSDs are really good. All had less than 5% RSDs except for the 0. The 0 was run to verify that we had less ABS counts than our 27 ppb, which demonstrating the fusion is able to accurately achieve low levels. So we want to see what that 0 point, it tells us how much carbon concentration is in our standard water that we're using there. So this is due to the nature of the 0 point. So when we look at the calibration results for our criteria was that we needed to be 3 nines or better. And that was achieved by doing the auto dilution via the system. And that's how we got the calibration curve presented in front of you. So we always recommend running check standards at the start and end of your schedule. So also take a note of the accuracy and precision here. So we set certain types of limits with pass-fail criteria of 10%. So our concentration here was 200 ppb. Our check standard read back at 185 ppb, had a percent RSD of 1.44, and it fell within our max and min of plus or minus 10%. And that's one great thing about this system is when you set a check standard, it will tell you if it passes or fails right here. If it failed and was outside of our window, our min or max deviation of plus or minus 10%, or even if our RSDs were high, we can have a failure. We can set up certain criteria within the system to show us what we want to do for acceptable data. And then at the end, we always want to make sure we finish the day off with another check standard. So we ran another check standard at the end of the day. As you can see, RSDs are less than 1%. It falls within our plus or minus range that we were looking for, plus or minus 10%. So we know the system started off in great shape, and now it's ending in great shape. So this is what the samples looks like from the reports. Obviously, sorry, it's a little small. I had to fit it all on the screen here. Remember, the testing criteria for this sample report was the samples had to be less than 7%, in which they all complied. So what we see here is bottle 1. We had a result of 1.45 ppm of carbon, and we had a reproducibility of less than 1%. For our bottle number 2, this had a low level result of 0.09 ppm of carbon, and it had a 3.0% RSD. Sample 3 was also below 1 ppm, which came out to be 0.78 ppm. Had an RSD of 4.1%. Bottle 4 had a 0.4 ppm carbon concentration, and it had an RSD of 3.4%. Sample 5 had 0.9 ppm, and it had 5% RSD. So what does that tell us? It tells us the bottled water that we're getting is very, very clean. So when we start looking at this, we actually converted to counts per part per million compared to ppm, so we can get a better snapshot of what we're looking at. The disparity from brand to brand was quite surprising. Obviously, we see certain types of distillation processes or purification processes will help remove certain amounts of carbon and other contaminants from the water. So most of these samples were actually lower than the tap water. So when we look at some of the tap water, I remember I said it's anywhere between 1 and 3 ppm. But when we start looking at this bottled water, the closest level that we got was brand 1, which is right at that 1.5 ppm level. But the other 4 brands were less than 1 ppm. So what does that mean? It plays a good clean role to prove that the water itself is pure and safe to drink for that. So when we start looking at key takeaways from this study, what do we need to understand, or what do we need to look at, is that indirect means of measuring water cleanliness. That's what TOC is in drinking water. We want to measure the cleanliness of our water. It's a catch-all. So any type of organic carbon, inorganic carbon, residuals, solvents, pollutants that might contain carbon in it, TOC is a catch-all for that. We can do fast analysis between 3 to 7 minutes per sample replicate on this system. So remember, the next technique or the next takeaway is the TOC techniques. Well, we got to make sure we're choosing our right technique for what our sample or what our industry is. So as I mentioned before, there's 4 primary types. There's combustion, UV persulfate, membrane conductivity, and spectrometry. So when we look at those, they all have benefits, they all have upsides, but the UV persulfate, compared to drinking water analysis, it has fewer interferences, lower background of carbon, and it has a lower detection limit, making it ideal to test bottled water, drinking water, and ultra pure water that is needed in our lives today. So once we chose the correct technique, we then take away from the bottled water. What do we look at here? Well, bottled water may be cleaner than tap water. There's a difference between brands, different filtration processes, cleaning processes. Basically, will be shows some differences. And then when we look at the different types of distillations or cleaning processes, reverse osmosis and vapor distillation techniques yielded the lowest results. So when we take that away, lots of software features on the Fusion make it an easy workflow. Allows you to put in your standards, put in your calibrations, put in your checks, put in your samples, start the system, and walk away. So as we continue to finish this up here, the bottled water discussion. What do we want to talk about here? Bottled water has a lot of different quality testing criteria than tap water. Tap water, coming from our taps, is tested against EPA standards, while bottled water is tested against the FDA standards. In our research, we could not find a regulated concentration for bottled water, although that some brands voluntarily gave TOC levels on their label. We ask, should there be more requirements for bottled water like we do out of the tap? That's a question that we ask, and we got to figure out where do we go to next with this type of analysis, because we always want to ensure that our water that we're drinking, the water that is coming out of our taps, the water that's in our bottles, the water that we are using for other processes is clean and doesn't have any harmful chemicals in it that could be detrimental. So with that said, I would like to take questions. If there's any questions about this webinar, please go ahead and feel free to ask them into the chat box. So the first question was, would drinking water have 0.8% sodium chloride as seen in this presentation? Not necessarily. It really depends on the source of water coming in. Sometimes your influent water, there might be certain types of salts or certain types of halogenated compounds in there. So we just use that as a reference to show the differences between techniques so that you can look at what type of interferences could be at play with different types of materials, and what type of detector or what type of system handles those better. If there's any more questions, go ahead and please enter them into the chat question box, and we'll be happy to answer them. If not, and there are questions that might come up later, please feel free to email us, and we'll be able to assist and help you directly and get those questions answered. If there are no other questions, we got one more coming in. Have you tested the acid? There are certain types of acid that we have tested or that we're working on actually. So we're looking at TOC content in sulfuric acid and different things like that. We'll have an application note coming out on that shortly. So I'll be able to answer that question much better in the near future and possibly on the next webinar or a webinar down the road. All right, if there's no other questions, I'm going to ask Shelley to end this recording. Thank you.
Okay, that'll conclude our webinar for today. Thank you all for attending.